You'll have noticed, for those of you that have been paying attention, that the title of the talk has changed somewhat from what was in the newsletter, and that was because we had a last-minute cancellation by Julie, which is unfortunate, but we will get her back at some point, but it won't be this year because the program for the rest of the year has been filled. But we're very lucky in that Teagan Blaikie's agreed to step in and give a presentation tonight. And for those of you that don't know Teagan, she's comes to us very highly recommended, I would say, and she's recently passed her thesis, and the reviewers of her thesis regarded the thesis she submitted as being in the top 5% worldwide. So it gives you some measure of the quality of the research that Teagan's been doing and what she's come here tonight to tell us about, which is about some of her 3D potential field modelling of the subsurface of complex maar volcanoes. So looking forward to hearing this, and I'd like to hand it over to Teagan to give us the talk for this evening. Thanks, Teagan.
Okay, so tonight I'm going to present some of the results from my PhD, where I've been working in the newer Volcanics province in Western Victoria and looking at some of the complex maar volcanoes that are out there and sort of collecting some gravity and magnetic data and modelling that to look at the subsurface structure of these volcanoes. So, because it's quite a young volcanic field, we don't see any subsurface structures of these maar volcanoes exposed, and they're all the subsurface structures are hidden by post-eruptive sediments within the maar craters. But most of the work that's already been done on the newer volcanics tends to focus more on the surface characteristics of the edifice, so looking at the crater morphology, pyroclastic deposits, looking at geochemistry, and it tells us about the eruptive history of the volcano, but it doesn't actually tell us about the subsurface morphology. So there's a need to take sort of a new and multidisciplinary approach to research and combine fields such as physical volcanology with potential field modelling to look at these subsurface structures and relate that to the eruptive history of these volcanoes. So within Western Victoria, there should be quite a high geophysical contrast between the host rocks that the volcano's sitting in and the maar diatreme, as well as any basaltic lava flows or feeder dikes within the vents. And we can really gain quite an improved knowledge of these volcanic systems by integrating geophysics and geologic data. So the newer Volcanics province is an active intraplate basaltic volcanic province, and volcanism spans from roughly 4.5 million years ago to 4,500 years ago. So the youngest eruption is at Mount Gambier, which is in sort of this province to the west of the main section of the newer Volcanics province. So the newer Volcanics is divided into 3 sub-provinces on the basis of morphology and geochemistry. So we have the Central Highlands sub-province up in the northeast up there, Western Plains down here, which overlaps onto the sediments of the Otway Basin, which is really important when we're looking at these maar volcanoes and considering where the water is coming from to fuel phreatomagmatic activity. So there are 40 maars that have been identified to date within the newer Volcanics province, and these range from quite small, simple, circular maar craters to very large. Some of the largest maars in the world are within Western Victoria, and these have quite complex craters, often with nested scoria cones, and are associated with multiple vents. Most of the maars are actually hosted within the sediments of the Otway Basin, and this is really important for fueling that phreatomagmatic activity. Now, in each of these volcanoes, what we see is the original crater rims preserved, but we don't actually see any exposure of the underlying maar diatreme. So we need to apply geophysics to image the subsurface structure. So if you don't know what a maar diatreme is, it's basically a subsurface collapse structure underneath the main crater, and it forms as magma rises as a dike intersects groundwater in the shallow subsurface, and this forms a phreatomagmatic explosion. And these explosions can occur typically at any depth, but they will only erupt when explosions are shallow, so greater than 200 metres depth. So these explosions can excavate a small crater, which then gets infilled with pyroclastic and host rock debris during the eruption. And as the eruption proceeds, this these explosion points can propagate downwards and occur at multiple depths. You did get dikes intruding within the diatreme to form these intradiatreme fragmentation zones. You get basically debris jets forming. So as the magma and groundwater explodes, it sends debris upwards through the diatreme. So it is quite a complex structure. And as the eruption proceeds, you get this mixing of material through the diatreme. So basically starting at the base of the diatreme, material just gets mixed upwards. And then when it's within that 200 metres to the surface and you get explosions occurring at that depth, that's when you actually get eruptions and material ejected out of the crater. So prior to actually going out in the field and collecting magnetic data and gravity data, I wanted to know what sort of geophysical signature to expect. So I needed to know this before I actually went out into the field so I could design a survey that was suitable for actually detecting these anomalies. So what we expect over maar volcanoes is we have a low density sedimentary and pyroclastic infill within the diatreme itself. We might see some denser basaltic feeder vents or feeder dikes within the actual diatreme, and then might have a layer of low density sediments infilling the crater. So what we really expect to see is a gravity low over the maar crater, and there might be shorter wavelength gravity highs within the centre of the crater where the Mars vents are. So this is what I've tried to represent in a couple of synthetic models. So the top two models are showing a shallow maar diatreme. So this structure is quite common in weakly lithified sediments like we'd expect in Western Victoria. And the bottom two models are for a sort of a deeper, more steep cone-shaped structure, which is, I guess, a diatreme you'd expect in a more consolidated host rock. So what the results of this shown is that we're getting gravity lows over the maar volcanoes with these very small, I don't know how well you can see from back there, but there is a very small local gravity anomaly here and a large one for model D up there. So what I was trying to find in my surveys was just that tiny little blip, and which I'm expecting to see structures like model B. So I had to be really careful with my surveys. So I collected gravity data at 15 to 20 metre station spacing through a number of traverses across these volcanoes, and also we just walked the magnetic data along those same traverses. So just a couple of photos from just field work. It was quite challenging conditions. The ground was very swampy, so it's not ideal for collecting gravity data, but we actually got some quite nice data out of it. So this is just the workflow I developed for actually interpreting these data. So there's many different strategies for modelling potential field data, and the workflow that I've sort of developed it focuses a lot on integrating geologic data, so looking at the pyroclastic deposits, looking at density and magnetic susceptibility, and combining all that information into the geophysical model to produce a quite robust results. So the method I've used is I've taken that geologic data, I've then constructed a 2D cross-section, and I've constructed those cross-sections along my traverses where I collected data, and then combine those together to create a 3D model, which I've then run some gravity and magnetic inversions on to optimise the property distribution and the geometry of the model. Because potential field models are non-unique and we can produce many different models, it's really important that we constrain the results. So I've also collected magnetic susceptibility and density data from the rock types that we expect to see and incorporate that into my model. Another thing we look at is the regional geology, surface observation, so especially looking at the lithic fragments within the Mars ejector rim to try and work out the depth at which they were derived, and then that gives us some constraint on the depth of the diatreme underneath. Also had a bit of a look at the stratigraphy, again to look at the lithic fragments and where they've come from, but also looking at the aquifers and where the groundwater is going to come from to actually fuel that phreatomagmatic activity. So what we have, Oakland maar is quite a simple maar volcano, and it's formed predominantly from phreatomagmatic activity. There's no real fluctuations between phreatomagmatic and magmatic activity, and what we have close to the surface is quite a good aquifer. whereas at Mount Lura and Redrock, we've only got minor aquifers with sort of thin layers of porous sediments, and then they're interbedded with sort of rocks with a low porosity or low permeability. So those two systems aren't getting as much water as say like Oakland, and as a result what we're seeing is really fluctuating eruptive styles or transitions between ferromagmatic and magmatic activity. So other things we can use to help constrain the interpretation is looking at features such as bomb impact structures, and that helps confirm where our vent locations are from the geophysical models. Also looking at base surges, the direction that we can derive the direction of the base flow from those deposits and work out again where they originated from, and that just helps confirm what we're seeing in our geophysical models. Also looking at the eruption styles, so magmatic eruption styles tends to occur quite shallow at shallow levels, whereas ferromagmatic is a bit deeper. So where we're getting fluctuating eruptive styles, like this is a section from Redrock, it's suggesting there is magma actually quite close to the surface, and it is just frequently fluctuating between those two styles, probably due to just a variable water source. So I've looked at a few different volcanoes out in Western Victoria, so I'm going to talk about Oakland, Redrock and Mount Lura today. So these are just their locations, just a few hours west of Melbourne, and they're all hosted within the sediments of the Otway Basin. So as I mentioned before, Oakland is quite a simple maar volcano. It's about 800 metres by 1,000 metres in size, hosted within sediments of the Otway Basin, and we see a predominantly ferromagmatic eruptive style. So this is the gravity data and magnetic data that I got from Oakland. So this top one, this is the VDI anomaly. You can see the black dots are the location of all my gravity stations, and the lines are the magnetic traverses that where we collected data. So what I've done in Model B is just remove that north-south regional trend you can see, and what we've got is just a gravity low over the maar with a sort of greater negative anomaly in the southern part of the maar. What I've done in C is just applied a high-pass filter to that data to try and amplify the short wavelength anomalies, and what I've found is these are actually very subtle gravity anomalies, but they correlate really nicely with the magnetic anomaly map. So if we have a look, these are just two of the sections that I produced, where I've got two coalesced diatreme structures. So the two anomalies indicate there's two vents within the maars. We're getting a deep diatreme in the southern part of the maar where we have that greater amplitude negative anomaly. Within the centre of the diatreme we have two denser vents, and I've interpreted these to be basically remnants of debris jets. So as you've got having explosions occurring within the diatreme, they are sending more juvenile material upwards, and that gets entrained into the diatreme. So we're just getting this zone where we have a high concentration of magmatic material, and that's why we're getting that density and the gravity and magnetic anomaly. And the two vents that we see have been confirmed by ballistic impact SAG structures and also the base surge deposits. So I combined a number of those sections together to create a 3D model. So A is my initial 3D model, and the little coloured dots up there, they're the model misfit. So there's still a little, where it's green there's a very sort of low residual, but where it's blue or red there's a little bit of misfit over the model. So I've run a Model B, just a geometry inversion to try and improve the shape of the diatreme, and that's improved the residual anomaly quite a lot. Then what I've done is I've taken the resultant model, which is the green surface, and then run a heterogeneous property inversion on that to optimise the property distribution within the model. And you can see we've got the sort of lower density around the edges of the lower density material around the edges of the diatreme, and the higher density material where we have a higher concentration of juvenile material within the actual vents of the maar. And Model D is a magnetic inversion where we're seeing basically similar results. So looking at the evolution I guess determined from the geophysical models, and also from looking at the deposits, is that we've had an initial eruption occur within the northern vent of the maar, and initially the depth of magma-water interaction has remained at quite shallow levels. Then the vent has migrated to the south as the depth of magma-water interaction is just sort of propagated downwards a little bit, and we're forming two coalesced diatremes. Moving on to have a look at the Redrock volcanic complex. So this is a nested maar and scoria cone complex. So this is just a lighter image over here. So we have quite a large maar crater in the south, and we've got overlapping that is a tuff ring. You can see the outline of that in the north, and then the complex has been infilled with some lava flows and also a scoria cone complex. I think there's about 18 different scoria cones contained within those two overlapping craters. So there was that initial ferromagmatic phase which formed the maar and the tuff ring, and then a later phase which filled the craters with lava and formed the cones. So this is the data I got from Mount Lura. So most of the data collection was focused on the southern parts of the maar because the town of Camperdown overlaps the northern parts, and there's also a couple of active quarries we couldn't get into. So that's why the data is just on the sort of the southern part of the volcano. So what we have, where we have this black dashed line, that's the outline of the maar crater, whereas the white dashed line is the outline of the tuff ring. What we see, the top one's the gravity anomaly, and we see the gravity high located mostly contained within the extent of the tuff ring, and that's where we're seeing the lavas and most of the scoria cones. And we have a gravity low located over the maar crater, and that's reflecting the lower density diatreme infill that's underlying that. The magnetic anomaly map is a bit variable, but we're getting a sort of a magnetic low over the maar and the magnetic highs over the scoria cones. So these are some of the models I produced from Mount Lura. So we've got the diatreme underlying the maar and the tuff ring, which have then been overlaid by quite a thick sequence of lava flows, and then the scoria cones. So combining them together, I produced this 3D model and then run some inversions. So this top model here is my initial model, and then I've run a geometry inversion on that to just optimize the shape of the diatreme. So it's made everything a little bit deeper than my initial model. Then run a heterogeneous inversion on that to optimize the properties. So you can, don't know how well you can make it out, but we do have a bit of a heterogeneous density distribution within the diatreme, but the density is actually quite close to what the host rock is, which is not surprising because there is going to be a lot of host rock lithics combined within the diatreme itself. So it's actually quite difficult to image, and I'll sort of talk about that in my sensitivity analysis a little bit later. So looking at the evolution of Mount Lura, we had an initial eruption forming a maar volcano in the south of the complex. We've then, the vent has migrated to the north to form the tuff ring in the north. Sorry, skip to the end. Then had some lava flows overlay the complex, mostly confined within the extent of the tuff ring, and then formation of the scoria cones. So moving on to Redrock. Redrock is one of the most complex volcanic centres within the New Volcanics province, if not the most complex. There are multiple maars and nested scoria cones. There's 40 different vents associated with this volcano, and they range from single vent maar craters that are about 20 or 30 metres in diameter up to multiple vent craters which are over 1.4 kilometres wide. So myself and another master's student have acquired gravity and magnetic data across each of the maars within the Redrock volcanic complex, and what we're seeing here is quite a complex geophysical response. So this is just looking at the central part of the complex, so just basically these four maars up here, and that's where I've sort of focused my PhD. And what we see this is the Bouguer gravity anomaly, but we've still got, again, a bit of a regional gradient in there, which I've removed in this figure up here. So we're seeing quite a variable response over all of the maars here. We've got a bit of a gravity low over Lake Petitulac here. We're seeing a bit of a north-south trending gravity anomaly, which you also see in the aeromag data. We're seeing a gravity high over that maar in the northeast there, and gravity lows over the other maars. This one here was a bit filled with water when we were doing the survey, so we've only got a few data points, so it's a bit hard to see what's going on there. But looking at the vertical derivative of the gravity data, what we start to see is, especially in this maar, lots of sort of short wavelength local gravity highs, and that they correlate quite nicely with the anomalies we detected in the magnetic data. So this is just some of the sections in the 3D model I've produced of this complex. So again, we're seeing lots of shallow diatremes with lots of intrusions actually within them, which correlate to those gravity and magnetic highs that we're seeing. Combining them together, this is the 3D model of the diatremes across the whole complex. And what we're seeing at Redrock is quite complex internal structures with lots of multiple vents. And this is indicating there is vent migration going on. And that's quite common in sort of weakly lithified host rock settings such as this, where you get material actually collapsing into the vent as it's erupting. It's blocking the vent, and then when it's migrating, causing the eruption point to migrate laterally. That's why we're seeing such a complex vent system at Redrock. And the complex internal structures with lots of intrusions is in part related to that, but also probably due to the poorer quality aquifers at the surface, and the system is actually not getting as much water into it, so we do have these fluctuations in eruptive styles. Looking at the inversion, so this is a heterogeneous inversion of this maar that I've modelled here, and what I've done in the inversion is basically taken out these vents and then let the computer run the model, and then it's actually seeing where it's modelling those vents. So they actually match up pretty well with what I modelled initially. And if you look here, we can actually see these structures sort of coming down to the main feeder vent within the maar. So again, just looking at a couple more 3D models that I produced. Again, complex internal structures with multiple intrusions and also remnant feeder vents. This is what we're observing across the complex. The broad shallow diatremes are indicating that we do have quite shallow eruptions, so that when I mentioned that freatomagmatic eruptions tend not to actually eject material out of the crater unless they're above 200 metres, the fact that we have quite shallow diatremes suggests that a lot of those explosions could be occurring within that depth, and we are getting a lot of material actually ejected from the diatreme itself. Looking at the evolution, this is just looking at the evolution of the Werra maar in the centre, which had the gravity high over it. So we had initial formation of the maar crater, then we've had dikes rise through it, and we've had these fluctuating eruptive styles, and they've actually formed a small spatter cone, which can be seen if you walk down into the lake. You can still see remnants of that cone there. But there's probably actually a couple buried under there, and then they have been later buried by lake sediments when the lake formed. So because potential field models are non-unique, and you can produce many different models with the data that you have observed. So this is just two different models from the Oakland maar that I've made. Both of them satisfy the observed gravity and magnetic data. So we've had to make a few assumptions in this model because I was unable to actually sample the maar diatreme. I've had to infer the properties based on what I've seen in the Mars ejector rim. So to try and reduce the ambiguity of this interpretation, I've just had to make sure that all my interpretations are consistent with all the information that I'm seeing, and then try and link my geophysical models with my interpretation of the eruptive history, both from the geophysics and from what's already known about the deposits. So my work's not about producing a particular model that's correct, and I aim to, and I have produced lots of models that highlight different features of the subsurface depending on what inversion style that I use. So I've run a bunch of sensitivity analysis just to try and determine what structures in the model are more sensitive to change, which ones aren't, work out how well constrained different elements of the model are, and also calculate M-member models based on the range of properties that I have observed. And I've done this because I've been unable to actually sample the diatreme itself to actually work out what the density is. So I've used the deposits as an analogue, but I can also determine what the geometry would be if we assign a different density and if it perhaps ranges across a range of values. So this is the models I've got of the Oakland maar. So A was my initial reference model, and C was the optimised model, which I discussed earlier. And these other models just show how the geometry of the diatreme actually varies if I change the density. So if we have a density lower than that of the reference model, I get a structure like model B, whereas if it's greater, then I get a much deeper diatreme like model E. But what is, I guess, consistent between all these models is we're still seeing two coalesced vents, and we're seeing a similar structure quite close to the surface, where we do have this sort of broad shallow diatreme close to the surface, and then as we sort of go, say, below 500-600 metres, we're getting a much steeper dipping diatreme. And this, I guess, this change between this broad diatreme and this steep diatreme is occurring where there's actually a change in stratigraphy within the basin. So it could just be that the next stratigraphic layer down is actually a bit stronger than the surface layer, so it's able to support these steeply dipping diatreme walls, and that's why we're seeing this kind of structure below that depth. So this is a couple more models I produced at Oakland, which I just spoke about, and then again Mount Lura. So my reference model density was 2.32. I couldn't actually get a successful inversion result over anything with a greater density than that, but the optimised version of that model is just slightly deeper than the initial reference. With a lower density, again, I couldn't get a successful model with anything lower than 1.92, and we're seeing a much shallower maar diatreme with that structure. But we're starting to introduce a few sort of edge effects just from inverting it with such a low density. So the next thing I've done after I've produced all those models is I'm able to actually estimate what the magma volume is during the eruption of these volcanoes. And this is really important when trying to constrain, say, the VDI Index, so how intense the eruption is. Just so more from a hazards perspective, if there's a future eruption, it's important to know the size of eruptions in the past. We already have high-resolution digital elevation models. There's a lot of LiDAR data over these volcanoes, and there's quite a few drill like groundwater boreholes, which I've been able to work out the thickness of these deposits, and also from a bit of mapping. And I've been able to calculate the volume of those. Also know the volume of the diatreme of the vents and any intrusions within that from the geophysical models. So using that, I can calculate the bulk volume of all those different structures, and then taking the componentry of the deposits as, I guess, an analogue for what's occurring again in the diatreme. So looking at the proportion of lithics, the proportion of juvenile contents, and also the vesicularity, I can then calculate magma volumes. So this is basically, these units are all in cubic kilometres. So we're seeing quite a high magma volume at Mount Lura, where we're getting, again, a complex eruptive history. We're getting quite a lot of lava flows and a lot of the cone forming event, which has produced all those scrotocones. At Redrock, again, we have most of the volume, magma volume, is contained within the maar diatreme itself, and then we've got a little bit contained within the cones and the actual ejectorium itself. So we've got a volume of, say, 0.18 cubic kilometres of magma associated with this complex, and 0.29 at Mount Lura. Oakland has got quite a small magma volume, so this is 0.04 cubic kilometres of magma. And this is also, it's another way of just, I guess, confirming how accurate our geophysical models are, because I can try and balance the deposits, the amount of lithic fragments that have been derived from the stratigraphy actually in the ejector rim, so I can balance that with what's the volume of the diatreme. So this is that's the volume of rock that's been disturbed. Work out how much is in the ejector rim, how much remains in the diatreme. Actually try and balance that out. So Oakland came out really well. We've only just slightly overestimated the volume of lithic fragments, whether that's because I've overestimated the volume of deposits or underestimated the volume of the diatreme. I'm not sure, but it balances out fairly well. There is a bit of a discrepancy at the Redrock volcanic complex. Probably 50% of the country rock is unaccounted for within my calculations. Whether that's because I've underestimated the volume of the diatremes. None of these calculations were actually able to account for the distal ash deposits, because there's so many volcanoes in the regions. When you actually look at the distal ash deposits, it's difficult to work out where they were derived from. So there could be a component of that. There's also multiple vents at the Redrock volcanic complex. So when you have a new eruption that's actually disturbing deposits that were previously laid down by earlier maar, so it's quite possible there's actually quite a lot of material that's been lost from Redrock just from the multiple vents. And Mount Lura actually couldn't calculate the volume of the Mars ejector ring, because there's several other Mars that actually overprint that. So it was really difficult to actually work out the extent of that and the volume of those deposits. So that's why there's a bit of a discrepancy there. But based on the calculations that I made and the erupted tephra that I've worked out, I've been able to work out what the VDI Index of these volcanoes were. So estimated these around VDI 2. I think Redrock and Mount Lura probably went up to VDI 3. It's really difficult to estimate because there's multiple events and we actually don't know how much time passed between individual events. If we had one event that formed over a day or two and then the system went quiet for a couple of months and then we had a new event form and that happened for the whole complex, then it probably didn't range above VDI 2. But if the eruption was relatively continuous, yeah?
Sorry, what is VDI?
So it's the Volcanic Explosivity Index. So when you have eruptions, they basically, it's related in part to the volume that's been ejected from the volcano, and also the height of the eruption column. So this just shows the volumes here. So VDI 2 is 0.1 cubic kilometres, and eruption column heights between, say, 1 and 5 kilometres, whereas VDI 3 is 0.1 cubic kilometres of, that's ejected material. It doesn't include stuff that's actually contained within the diatreme, just what's been ejected. Okay, so we're estimating that about 2. So that's quite a moderate, like small eruption. VDI 3 is a little bit higher. We have seen eruptions within the newer volcanics. So Mount Gambier, Joshua van Otterloo, who also did his PhD at Monash, estimated that at a VDI 4. So that's equivalent to that volcano in Iceland in 2010, which caused chaos across Europe. So we could potentially have an eruption that large again in the future. But the ones I'm working on are probably a little bit smaller than that, and a VDI 3. So they would be equivalent to the eruption of Ukinrek. So this is a couple of Mars that erupted in the 1977 in Alaska, and they produced eruption columns up to 6 kilometres high, and dispersed ash at least 160 kilometres from the vent. So there is quite a lot of potential. If there's another eruption within Western Victoria, there is potential for that to impact on modern infrastructure. So all that ash is going to come west over Melbourne, which is going to affect air quality and air traffic and all modern infrastructure that we have. So just in summary, my geophysical modelling has identified complex maar diatreme structures. What we're seeing is shallow maar diatremes with multiple vents, and these are related to the weakly lithopod host rock. Where we have the water saturated sediments, it's in some ways preventing the downward propagation of explosions, so it's allowing them to remain at shallow levels, say above 200 metres, where it's actually going to eject a lot of material from the vent. And that host rock is also contributing to the vent migration that we're seeing in each of these volcanoes. Where we see evidence of these longer wavelength, low amplitude gravity and magnetic anomalies, this is representing the debris jets being entrained within the diatreme, and these form some subvertical zones with high volumes of volcanic debris within them, and they represent the vents of the maar. Where we see high amplitude, short wavelength gravity anomalies like we're seeing at Redrock and Mount Lura, It's caused by the groundwater drying up, which has allowed the magma to rise to the surface and erupt in a more magmatic style. So just the hazard implications of this work is that my geophysical models have been able to identify that these maar diatremes are actually quite shallow in their nature. There's some experimental work that's been done that looks at the depth of these explosions and how much material they're actually going to eject from the vent. So we have these deeper explosions, greater than 200 metres. They're really confined by the crater and the overlying maar diatreme field. So when you get explosions that deep, they're actually unable to erupt or eject a large volume of material from the crater. But where we're getting the shallow explosions, like what I'm observing in Western Victoria, they're actually more likely to erupt and will disperse volcanic ash over a much wider area. Thank you.